introducing today's speaker. So thanks everybody for joining this AI seminar. So we are having Professor Tomer Weiss from NJIT. So Tomer Weiss was before he joined NJIT as assistant professor, he was a research scientist with Wayfair, and even before that, he got his PhD degree from UCLA, where he worked with Professor Dimitri, and he received the Best Paper Award from ACMC Graph Conference on Motion in Games, and also he was a finalist presenter in both ACMC Graph Thesis Forward, Fast Forward, and also the ACMC Graph Asia Doctoral Symposium. And so I think his main research interests include computational interior design, collective dynamics, and interactive visual computing. So today he's going to share with us lots of his recent research on creating virtual spaces with computational interior design and also deep learning. Thanks.
Okay, thank you, Moha, for that nice introduction. I'm gonna share my screen. So we're just gonna do a quick check. Can you see my screen? Okay, good. So I'm gonna continue, and I'm just gonna hide all the video because it's kind of invading my slide. So, so great. So hi everyone, I'm Tomer Weiss. I'm gonna talk today about creating virtual spaces with computational interior design and deep learning. So you can see this beautiful space, and imagine this beautiful space is something you want a computer to create for you. How would you do that? So that's the gist of my talk. So how did I get here? So I did a couple of gigs in different organizations, as you can see. I did get my PhD at UCLA. Before that, I did spend time with Wayfair, Autodesk Research, and A9, which is part of Amazon, doing all kinds of machine learning and research work. And my group at NJIT focuses on these two big areas of graphics and vision. And here you can see kind of like a teasers of the types of research I work on in our group. So, and the common thing of all of this is it's visual and interactive. Okay, so other than this related domains that may appeal to part of you, because I know that USC has a large group of AI researchers. I also know that you have a large group of robotics, architecture, HCI, and all these kinds of researchers. So all of these kind of topics are related to the research that I'm going to talk about today. Specifically today, I'm going to talk about my research in design and computational design, and specifically these two works about deep learning for style estimation and optimization methods for kind of these kind of virtual content creation. So the two big kind of questions here in this topic is what furniture and objects to place in a room and where to place these objects. So these objects seem these kind of questions seem pretty easy, like not that like everyone can answer that, but imagine you're trying to teach a computer these concepts of what and where of furniture, and it becomes really hard really quick. So I'm going to talk about this pretty soon. So now let's start with motivation. I'm going to hammer down a lot of motivation of why this is important and why this is like interesting. So first of all, interior design is complicated. For example, you have a couple of pictures over here. You can see like a funny picture of a person put the sofa like that in the middle of the room. Obviously it doesn't look great. And there's all kinds of these rules. So this looks nice, but this doesn't, like with this carpet over here, not like reaching the sofa. And this, like, for example, here we have like a weird furniture popping out in this configuration. So we obviously agree that interior design is a complicated process. There's a lot of professionals you can hire, so you can get like very kind of cool interiors like this one. Another motivation is in retail. For example, let's say you're trying to sell like stuff online, like objects, decor, beds, baths, and so on. So you have a website and all of that, and now you need to obviously sell it. So the first thing when you're selling anything is you need images, right? Like you can't just have a text and that's it. So here, for example, we have this kind of an image of this like object over here, and or like a nightstand over here. So this kind of continues and continues. So obviously, if we don't have any of these images, it's very hard to understand what you're selling. So imagery is very, very important in like these kind of retail, especially internet retail kind of companies. And to create this kind of imagery, obviously, one way you can do it is you can either just hire a photographer and like take a lot of pictures, but that becomes kind of silly, right? Really quick. So if you hire this photographer, then you obviously need to do like this kind of maneuvers with furniture, staging, moving them. It's like time consuming, it's manual, it's like not elegant. It's not nice. So the typical way people do this kind of staging and taking pictures for these websites is they usually create these scenes online virtually. And in this way, assets can be reused and kind of reused quickly. So here's a quick example of how you create like a 3D asset. So here we have an artist. The artist is trying to create this chair on the left-hand side, and you can see the process on the right-hand side. So notice this is not like a very quick process. It's very slow. It's time consuming. It's something you need a professional for. You need to hire this artist. You need to pay them. You need to pay them benefits. It's not easy. If we go on, we can like kind of scale this up to entire rooms, but then you see how many different configurations you can have for furniture when you just try to put it in a virtual room. You can have, you know, smaller furniture, bigger furniture, different textures, and so on. So this kind of continues into like various kind of complexity, as much complexity as you want for these kind of virtual rooms. Okay, and eventually you get a very nice rendered result that looks like this. This is a virtual room, but it looks kind of real, right? So this looks pretty nice. You would be very happy living in this room. So so that's the one motivation. Another motivation that is also related to this, why do we care about computational interior design, is gaming. So I don't know if you know, but gaming is pretty big. It eclipsed all the other entertainment industries a couple of years ago. And if you just look at a typical gaming scene, like here, we have like a hero character. We have like the barrel. So just creating this barrel costs $940. So it's kind of silly. And if you scale this up to the entire scene, it's about $200,000. So how did I get this number? So first of all, so I'm assuming you need to pay an artist about $60 an hour, which assumes his like salary plus health benefits and all of that. Then this is like the amount of kind of multiplying by the amount of time it takes to create this car or all of these assets, you get this cost, which is like a lot of money. And also gaming.
Tomer, sorry to interrupt. I think your own image is blurred from the sunlight.
Oh, okay.
You probably can turn yourself around.
Now?
No, it's still blurred.
Oh, so
I mean your own image. That's like your camera.
Interesting. What about now?
No, yeah, no, that's clear. Yeah.
Okay, thanks. Cool. Okay, yeah. So let's hide. So let's continue. So as you can see here, if we look at the cost of creating games over the last couple of years, it's rising exponentially. So all of these things are adding up really quick, and there's obviously a place for more computational need for algorithms and computers to help with these kind of tasks. Okay, so let me just quickly move this here. So again, this is a slow process. You still need the artist in the loop and to create these assets, and creating these assets is really, really slow. As you can see here, you have like this is not an easy UI to use. There's a lot of knobs and kind of buttons you need to push, and you need to know what you're doing. So because of that, and because of this kind of complication in this area, there's a lot of research going on how to help artists, game creators, retail, and other people to do this kind of work. So for example, here, this research spans from synthesis, which is like, how do you create these scenes, style, on how you estimate like what 3D object is similar to another 3D object, light, on where to put the light in the room in the way that it makes sense for the scene that you're trying to capture. And also composition is basically where you take pictures of that virtual room so it kind of makes sense and appeals to clients and so on. So here, this is like something IKEA is using, for example. Okay, so today I'm going to focus on two specific aspects of my research that's relevant to what we just saw. All that motivation is what goes well together and where do I place things. So we're going to start here on where do I place things. That's the first question. This is the topic I addressed in this research paper, which is the fast and scalable position-based layout synthesis. We published this in IEEE TVCG in 2018. So the main contributions of this work were a novel optimization-based framework for kind of placing furniture for you. It's based on physics, it's interactive, and you can do a lot of large-scale layouts in real time. So you can get virtual spaces in seconds. So I'm gonna just kind of drill down on how do we go about to do that. So if we first of all take a look at a virtual room, we can see here, this is a typical, like say, living room. There's a lot of things happening here, and let's look closely at what's happening. So first of all, we have this distance between the plant and the wall. So why do we want that? Maybe we don't want to place a plant in the middle of the room, right? Doesn't always make sense. We also have like a pairwise distance here between the chair and the table, so that this chair should always probably be next to that table. We also don't want any overlap, so we don't want this kind of virtual plant to be colliding with this sofa, so we want some kind of space between them. And we also want to observe some kind of aesthetic constraints. For example, here the sofa should directly look at the TV, and there should be some symmetry between these chairs and the sofa, so this looks kind of nicer from a human standpoint. Okay, and the common thing for all of these constraints is they're geometric. So basically, you can use geometry to explain them to the computer. So here's one constraint. So for example, this is the simplest constraint in the book. So we have a chair and we have a table, and we want it to be at this distance d. So if we abstract, like say let's like put the chairs aside and pretend they're particles. So these particles should be at this distance d away from each other. And we can also use this mathematical notation to define constraints such as these two particles should be no closer than a distance d from each other, like this one. So I just replace the greater than sign with the equality sign with the greater than sign. And then we get something like that. Okay, so now we saw this constraint. Okay, so now what do we do? Like, we still need some kind of machinery to actually use it in a computational way to get what we want. So what we do is we resort to this framework. So this framework is called position-based dynamics. It has been kind of widely used in simulation, in graphics, in gaming to do these kind of real-time optimization, basically, of elastic and deformable objects. So you can see here, there's like a net and there's like a lot of rocks. And you can see in real time, it kind of deforms and adapts to the positions of all these like stones and rocks in them. And you can imagine this net is basically composed of constraints between particles. So all these like small the points are basically particles, and these like links are the constraints. And so why actually we use this and not something else? So first of all, this framework was kind of proven to be useful for real-time simulation of tens of thousands of particles. So it's very powerful and very quick. It's easy to control, so you can easily define constraints in whatever geometrical form you want. And what we're going to see now is how does this actually work in terms of derivation and correction. So okay, so mathematically, constraint is what we saw before. So now the task in hand is to kind of figure out how we should actually move the objects around or the particles around to fit this constraint, so to make it happy. And when I say to make it happy, that means to make it equal to 0. So what happened is basically the furniture is not in the right position. There's like some correction, which is this delta x over here. And we want to resolve this in a way that the constraint is happy. So the easiest thing to do is to find this delta x, this correction, is to take the gradient direction of this constraint and to move it along the gradient. So the gradient, basically, if you know math, it's kind of like the derivative of this constraint. And usually derivatives you move kind of towards the minimum, right? So now the question we need to know is how much to move it on this gradient. So the question is, what's this lambda over here, which is the scalar? So luckily, we can easily know what that's lambda by just using a couple of easy tricks, which I call copy paste. So here we have this information, and we also can just copy paste this definition into this definition. And that's how we can get a definition for lambda. So now we supposedly have everything we need to know about what the correction should be and to make this constraint equal to 0. Okay, and I will explain this a bit more. So so obviously this was the simple scenario, and we can make this a bit more complicated. So for example, you have a heavier object or a smaller object, so you can assign kind of more knobs and tweaks and parameters to control this optimization framework. For example, here I assigned weights to different particles. So for example, a larger sofa has more weight than a smaller sofa in that distance constraint. I can also define more things like a stiffness, for example, like K over here. So K is between 0 and 1, and it controls how quick it will kind of adjust to that optimization maneuver. And obviously all of this we can just, so if you have an object with a couple of constraints, we just accumulate all these corrections to find the final correction over here. And so if you were confused about all the math we just saw, I'll just make it very simple for you. Assume you have two particles. What this math tells you to do, you just draw a line between their centers and you put them back to the distance you want them to be. That's all. This is all what this map does. So if it was too hairy for you, and you can imagine this, you can do the same thing with these furniture objects. And you can imagine also we have like a network of furniture object or a graph of furniture object constraints, and these can all move along in the way that we want them to move to satisfy these constraints locally. Okay, so a lot of talk. Let's see what actually is happening here. So let's move to a result. So this is like a first result that I like to show. It's kind of large scale. You have like more than 200 chairs over here, and it looks kind of nice. There's a stage. We can see the chairs are looking towards the stage, and we created this scenario pretty fast. So what actually is happening here? What are the constraints here? So one constraint is the clearance here. So basically, I told the framework to not place any chairs along this kind of area. So that area is clear over. So on the other hand side, that's like symmetrical. We also told the framework not to basically place chairs at a certain distance from the stage. So each chair in a tier has its own distance to the stage. We also told the framework not to collide each chair with another chair, so there's no overlaps. And but if you kind of take a closer look here, it kind of looks a bit weird, right? It doesn't look exactly like a theater. It looks kind of sporadic. It doesn't look symmetric or robust or organized. So can we do better? So that's the question. I'm saying yes, we can. So here is like a difference in the same scenario, but kind of more symmetrical, organized. So what we did here was just had chair tiers, and each tier is basically has its own constraint, kind of geometrically. And we just, based on that, we just assign them to belong to that tier and adjust according to that position. And the constraint that we have here is, again, the clearance and the tiers, and also the distance between these tiers. I think someone raised their hand, and I want to be nice.
Yes, hi, Tomer. This is Keith. I had a question about whether this can be done in real time, or is this something one has to program with, say, inline commands?
Okay, so the result is in real time. The inline command part is basically something that you basically as a user need to tell the computer what you want, right? So you can either use inline commands to do that, or you can use a user interface. Actually, we did do a user interface in later research that allows you to do this kind of in real time. The optimization procedure itself is pretty quick. It's this specific scenario is about 2 seconds. I will show more results, and maybe you have more questions or not, and you can kind of follow up on that later. Does that make sense?
Yes, thank you.
Okay, cool. So okay, so obviously I'm not the first one to do this kind of research. There's a lot of work going on. I'm going to talk about this, but I'm going to compare it first and mainly to these two works, which are called Make It Home and Interactive Furniture Layout Using Interior Design Guidelines. So the way these works address this problem of placing furniture in a room is they do it using this kind of probabilistic method. So here we can see what's happening here. Basically, you have a room configuration of furniture, you shuffle it around and you find a new configuration. If it's better, you keep it. If it's not better, with some probability, you keep it. So this is kind of a probabilistic approach called Monte Carlo Markov chain, if you heard about that. And this is what's happening, basically. You're just kind of moving around this kind of landscape and trying to find the best configuration of furniture energy-wise. So this looks pretty neat. This looks also nice. Why is our solution better? So I'm going to get to that in a bit. Here you can see the shuffling kind of their work, of the furniture around. So why is ours better? First thing, it's because it's a lot quicker. So you can see their work, and we kind of implemented just to see. It takes about 163 seconds for this picnic layout, and you can see the shuffling going around, and our work is a lot faster in that regard, 4.7 seconds. We also had like a living room layout like this one. This is an imaginary living room, but you can see it's just a lot quicker to get the same results or similar results. Another problem with their work is it's globally optimized. So it solves like this global energy configuration problem. And you can see it doesn't have any knowledge of how to resolve these kind of like weird kind of collisions. So it doesn't know how to do that. There's no distance notation kind of that can quickly resolve it. So that's another problem here. So, okay, let's assume we have this work. It's great. We can use it. Now what? So one application is probably to just show you furniture in a room setting, right? So this is what we did in this CVPR workshop paper. We kind of took this idea of say a user takes an image of some kind of space, or you have an existing image, you have this markers, and you just want to see how furniture looks like in the room. And you can do that with our work very easily. You just like have to set up the plane and the marker, and you can see the furniture. So that's kind of nice. Our work is not that, there's a couple of limitations. That's what I wanted to really importantly say. It's not like one solution solves all. So what I did kind of sidestep here is the user has to select the furniture and all the kind of specific objects you want to put in the room. So that's like one limitation. Another limitation is the user has to define these constraints and placement rules, which obviously, if you're a novice user, it's not as easy, right? But luckily, for this part, I will show another work that deals with this specific component of the problem. And for this part, I'm going to address it now in the next slide. So what we did, we actually built a user interface that allows user to quickly kind of place furniture using these templates. And that will kind of, so this user interface basically allows you to kind of quickly use our framework to create furniture styles or designs and so on. Okay, and don't have too much time to go on this work, but you can see my website for more details. Okay, so deep learning. Deep learning is very important in this area too. I don't want to sidestep it. There's so much research going on in deep learning and how to use deep learning to synthesize rooms. Amazing. This is only a part of that work. The main problem with deep learning research in this area of synthesis is the results are only as good as your data set. So if you say you never have a kitchen in your data set, they could never synthesize kitchens. It's very hard to explain to the deep learning network what is a kitchen. You don't have a kitchen. Also, if you don't have a pink sofa in your data set, the framework cannot ever synthesize a room with a pink sofa. So you're only as good as your data. The other problem with this work is it's not interactive. So there's no way to kind of, people basically use this to just spit out results, but there's no way to kind of manipulate the results. So there's no kind of some kind of user fine-grained control over the results. So basically deep learning just spits result and it's not interactive. Also, this requires a GPU. So if you don't have a GPU, good luck, you can't do this work. You can't even run it. So that's the problem with deep learning. It's really good work, but there's limitations. And another big limitation is that this work relies on data, but that data actually is now overly in like legal contention. So there was like a big drama about Facebook was being sued by this company from Estonia about stealing their data. So what that means is practically all this synthesis work is not available because you can't get hold of these data sets that is used to synthesize these results. So that's just for you to know. Okay, so we saw kind of a couple of approaches on how to place objects in a room, but now let's kind of resort to this next question of what to pick, and is it style or color compatible? So, and this is basically the part we're going to talk about now. Okay, so here in this part, we first try to do a very, very simple problem, very simple. So we try to understand, can the computer be taught what is a room style? So in this simple problem, first of all, if you look at these images, right? Just look at these images. We have, you can immediately see like there's one room that kind of pops out. That's a bit different style-wise. Clue, this is this room over here. So maybe if we can see it and it doesn't take us too long to see this different style as humans, maybe the computer using computer vision algorithms, deep learning can do it as well. And that was the task in this work. So what we did is basically given an image, classified style, very easy. Classify, is it like this style or this style of room? And we started with these two simple styles, which are traditional and modern. So why these specific styles? Just because when I was working with Wayfair, that was the big chunk of the catalog. So there was either traditional looking rooms or modern looking rooms. So, okay, so let's just train a deep neural network to classify images according to this style. So we actually did that. We used, so the input here is like images with these labels, like traditional or modern. And we used the Svigidin network to kind of just predict style, and it just spits out if it's modern or traditional here. So the nice thing about this, it worked pretty well. It worked pretty well. It's like 88.7% for style. That's like amazing in my opinion for a computer to understand what style is. So that was great. Now we said that this was only for two styles, right? So can we make it work on more styles? So we kind of extended it to two more styles here, cottage and coastal. So the accuracy went down a bit. It was 81.2. So we kind of hypothesized that this is because that maybe some styles share visual features that like are common also in other styles. So maybe this is not the best way to do it, but still it looks pretty good. And I can show you some results over here. So for example, what we did is, this is one experiment. We had like an input image, which we see here on the left. And this input image is something that was already went through the network. It was predicted to be of a certain style and all of that. Now in the network, we used a certain layer of the network to extract like some kind of array of embeddings. So basically just like an array of numbers. And using that array of numbers, which is internal to the network, you can kind of have some idea of what style is this in this kind of a more generic sense of not just like more traditional or modern. It's a kind of more generic sense because it's like basically an array of vector of numbers. And using so this vector is called embeddings. And what we did is we kind of found the nearest neighbors in that embedding space that are closest to this image. And what we can see here is, so given this like sofa here in this room, we actually found a lot of nicer, similar style rooms, in my opinion, at least. They look very similar, which also have sofas, and they also kind of look modern, as you can see here. And also this kind of works the same here with this desk, or side table. So here you have the desk or side table. It's kind of like more traditional maybe, and also spits out a lot of like traditional looking images, which is great. Like, so I think this is kind of knows what it's doing. It kind of works well pretty for our purposes over here. So then we run a couple of more experiments, and we just did classification experiments to see what's happening. So here, the network classified this as modern, which I agree, it kind of makes sense to be modern. Over here, these are traditional. They look very traditional to me. And here in the middle is what the network was confused about. So obviously, if you look here, I as a human I am also confused what this is. So this is kind of like a bit kind of weird, like murky. I'm not sure if it's like a traditional or modern. And this one is kind of just a weird bathtub. And this, I'm not really sure what this is. So I'm confused too. I don't really have a hard and kind of fast opinion what this actual layout style is. So I agree with the network. So it's okay to be mixed, in my opinion, in this specific case. Okay, so we saw a way to understand and classify style, at least in the sense of like 1, 2, 3, or maybe 4 classes. It kind of gives us good results, but maybe we can actually do it for actual furniture, not just the rooms, but maybe the actual furniture objects that we have images for. Maybe also 3D objects. So the next research that we did was over here, where we had the task at hand was, given a 3D model of some furniture, what is its style and how can I suggest similar style furniture that fit that 3D model? So again, this work is not done in a vacuum. There's a lot of ongoing work. It's a very active area. 3D shapes and all of that is very active in many, many communities, CVPR, ICLR, NIPS, SIGGRAPH, and all of that. So there's 2 main approaches over here. So one approach is using the 3D model geometry to understand its style. The other approach is using image-based to understand an object style. And I'm going to explain what this actually means. So most of the work focused on geometry. So geometry, what I mean is basically there's like, imagine you have like only the object itself, the pure geometrical features of the object. So there's no color, no kind of texture, nothing. You basically have like all the objects are in the same color, and that's it. So it's obviously very hard to work with this to understand style, because style is a lot more than just the geometrical curves and all of that of an object, right? There's a lot more style information you can see in the picture in this image than just the pure geometrical features. And you can see here a couple of more ideas of what I'm talking about. So so that's the problem of pure geometrical based features. If we go to the other side, image-based approaches. So these image-based approaches were what they did, and they kind of just use images of furniture, but in this kind of very isolated, pure rendering. So here you have like this sofa or this chair in this very kind of isolated context. It's kind of hovering in like a space. So you don't really, it's kind of hard to understand what its style is, right? You don't even know the context of this picture. So it's kind of difficult to understand what's the concept of style over here. So what we suggested to do instead is just kind of to use these like curated scenes where you have sofas and you have like this decorations around them to and use that idea to extract style of the object. So here you can obviously see a lot more idea of what style is given this kind of context of the scene. And also this works the same with this kind of sofa. So you can obviously immediately see the difference style was between these two sofas and what kind of scenes would they be used in. So, okay, so let's start. So how did we do it? So first of all, we needed to collect data because we're going to use a deep learning approach. So to make things a bit simple, we kind of focused on 4 major styles, which are modern, traditional, again, cottage and coastal. And we had collected about 670K images, and each image was tagged by 10 experts. So given this image, you have 10 experts, 10 different people tagging it what style it is. And now after we did that, we got a bit confused. So you can see here, like given this image, six experts tagged it to be traditional and 4 tagged it to be cottage. So I'm really not an expert and I'm not really sure what's happening here, but I can agree that this could kind of be split between 2 different categories, right? So this problem is not only for this picture, this is like a wide occurring problem in a couple of the images in our data set. So we actually saw that if you look here on this table over here with the green and the red, so the red area kind of denotes how much confusion is among experts. So for example, experts were confused between traditional and modern like about 46% of the time. So that's kind of a lot, right? And there's like other kind of style kind of confusion, cross style confusion between these 2 different styles. So given this, maybe discrete labels are not the right way to understand style. Maybe you can't really associate style with one discrete label. Maybe we need to do something else, something different. So what we did is we used comparison labels, and I'm going to explain what that actually means. So here, the simplest way to look at it is like, you have 2 images and each of them have all these kind of labels, right? So one way to basically understand what style there is look at a specific style, say traditional, and see if in this specific style segment, these 2 images, which one is more traditional, right? So you by just comparing this like apples to apples, oranges to oranges, you can get a better notion of what style is. So you just compare this in the traditional sense, and just compare this in the cottage/country sense. And you can just continue doing this with Siamese networks. So, and we're not the first ones to suggest such framework, such comparison label. This was already used in other contexts like medicine, recommender systems, and so on, because it's just like more, it was shown to be less variable and less noisy. So like mechanically, we use the deep Siamese neural network, again, VGG, and these are the data details you can look through and see that we use to run this learning. So on first looks, we just try to estimate, see what the network did. Did it make sense or not? Does this comparison label scheme make sense? And yes, it did make sense. So it make a lot of improvement over the discrete label. And you can see the accuracy over here. So average, we had like about almost 80% accuracy with these comparison labels versus the traditional approach, which is kind of like 70%. And this is like a bunch of other results we gathered over the our experiments. Okay, so this is kind of a lot of bland numbers. How can I actually use this? So now that we have this machinery that can estimate style, so this is what we have. We can look again back at the embeddings and maybe use the embeddings somehow to estimate the furniture style. So let's take a look at these embedding vectors. So here we have a sofa, and we have this chair, and we just run this through the neural network, and out come these embeddings, and these embeddings are somewhere here in this embedding space. And this is a process we can do for each image. So we can run a couple of images here, and we can get their position in this embedding space. So this guy lives here, this guy lives here. And what we can do is, given this machinery, we can now find kind of the distance space style-wise between different images. So for example, this green and blue objects are kind of close style-wise because the distance here is lower than the other objects. So, so this is nice for images, but maybe you can just extend this to 3D models. So assuming we have a 3D model, we can now find all the images this 3D model is associated with in our database. So this model is associated with this image, and this 3D model is also associated with this image and this image. So now if we want to find how this 3D model is close stylistically to this 3D model, we can just use this image distance, right? So we can just find which images are the closest kind of in this embedding space. And that closest images will tell us how close are these 3D models kind of stylistically. So that's the idea. Okay, so now does this make sense? Question? I heard someone. No, okay. So how do we know if this makes sense? So first of all, what we can do, we can just kind of generate these kind of compatible and not compatible styles. So basically, what does this mean? We kind of like find all the accent chairs and side tables, and just kind of just permute over all of them and find which one scores lower or higher going to this distance metric we just showed. So this is the equation over here. So basically, we just kind of sum up the distances between the furniture, between the embeddings of that furniture. And we can see that the results that we get over here are they kind of make sense. So here, this kind of looks neat stylistically. This looks a bit kind of quirky, a bit awkward. And I would agree that these two guys kind of make more sense than this collection of furniture over here. And there's like more results. So there's a couple of results in the paper, you can see them. Here, this is also more compatible. Over here, this desk, which is kind of brownish, and these two chairs are kind of very similar in style. And this is less compatible. You can obviously see this is kind of weird, like this chair doesn't really belong to this configuration. And similar kind of for this lower collection over here. So another more experiments we can do is we can kind of just, given this query 3D model, we can kind of just find results that are like most compatible, given this embedding and all of that we just discussed. So given this coffee table of here, you can just say, okay, give me sofas that fit this coffee table. And this just gives you like most compatible, least compatible, and so on. So this is the most compatible one, and the least compatible one is over here on the right, that fit with this table. Okay, so we saw how to use this embedding scheme to kind of find various compatible furniture. What else can we do? So we can actually kind of design scenes that are style compatible according to what the network fix is style compatible. So here's an interactive example. So what we did here, we kind of just have the user kind of select the furniture object, and the user can, based on that selection, it just kind of searches the database and finds the most similar style furniture that are compatible with these existing sofa and these two chairs. So, and that's the existing in terms of the distance in the embedding. And as you can see, it kind of is nice. It kind of makes sense, at least color-wise, stylistically. And you can continue doing that, and you can even change other objects in the room. And this is what I like about this is like a lot nicer than just manually searching or using text to search like your big catalog of items to find what's most stylistically compatible with what you have. So this is kind of a nice interactive application of this kind of research. Okay, I'm going to continue now. Okay, so other than that, just creating scenes interactively, kind of in real time, we can also use this to enable 3D artists to work more efficiently. So what we did here in this kind of setting, we had users just had users select a seed furniture. For example, say you really want to create a scene with this chair. So we filtered out all the furniture that was not, say, in the top 100 or top 200 closest to this chair. So you only get the objects that are close proximity-wise in this embedding space. And you can only use that objects to create your scene. And you can see it kind of gives you the artist's ability to create statistically compatible scenes. So they kind of look a bit nicer. And it's a lot more efficient. Like say, if you don't know what the catalog is, catalog has like millions of items. So if you just have to work at 100 or 200 items, it's a lot easier to create scenes than if you have to search manually over like a million items to find something that really fits what you're trying to do. Okay. So let's conclude this research. So we saw how to create furniture style compatible scenes. We saw that styled images contain a lot more information than like these pure renderings. And we saw that these comparison-based approach is kind of nicer in terms of like learning and how to understand style, at least from a computational standpoint. Final remarks. So I'm just going to conclude what we saw so far today. So we did see a CME's deep learning network to find these similar style 3D objects. We did learn how to classify room style according to these notation of style. We saw a method to synthesize furniture layouts, and we have more research coming up really, really soon, but not yet. So it's not public yet. I do want to thank you, all my collaborators. This is almost my last slide. I hope I was not going too fast. A lot of collaborators from all the organizations I worked in, from NGIT to A9, and some of their names over here. I want to do a quick shout out to another USC researcher that should be doing a postdoc right now at USC. Her name is Ilka Yildiz, so you can reach out to her if you want to talk more about this research. I also want to advertise a workshop that I'm hosting and organizing along with other researchers. It's called IEEE AR and VR. So if you're a researcher working on AI or animation or VR, this is a good place for you. So this is a small list of topics. There's more on the website, and you can easily submit your work here. Okay, and that was the last part of my slide. Thank you. I really don't have anything more to share. I think I need to go back to my slide work again. I kind of lost it. Just give me 1 second. Here. Yep, so that's my last slide. So it was a bit quick. I will now take your questions, or if you have any question on the slide just before, that'll be fine too.
Yeah, thanks, Tomer, for this very exciting talk and also very beautiful slides. And it's actually very exciting to see there are a couple of familiar names in your list of collaborators as well. So I'll start with one question of myself. So I wonder if you have considered some technologies like disentangled embeddings of, let's say, those 3D models. My understanding is that you need to create a latent representation space for those, let's say, furnitures, but kind of differentiate between their styles. So that actually makes me think about some ways people, for example, in natural language processing, there are often this kind of technology in which you separate the embedding of a piece of text into two parts. A part of it, you throw it into let's say, either domain discriminator or syntax discriminator, and that discriminator is will also interact with the main task model through adversarial training. So in that case, that part is going to be either domain invariant or syntax invariant based on the training objective. Then the other part will be domain specific in that case. So in your case, does it make sense to, let's say, separate the embedding into two parts? One part could be style specific, the other part is style invariant, and then
Yeah, so so first of all, I like the way you're thinking. I like the way this is going. The problem, I'm not sure how to actually do that with the data that we have. So in terms of like images, how would you separate the embedding? So the only way right now, the only way I'm thinking of doing something similar to what you're suggesting is you have this network and you maybe just train it to kind of find like types or something, furniture types or something in the image or whatever the data is. And then you train another network and like you basically, that network is maybe focused on style, and maybe then you do some kind of mathematical manipulation where you just kind of subtract the embeddings of the type from the style or do something like that. And then maybe you get like pure something embeddings. Is that what you're talking about? Or
yeah, that's something similar.
Yeah, so it's quite the thing is like we do know how to define types. Style, so I think we need to drill down a bit on what it actually means on having like what is style, because style means a lot of things, right? It can so every style has a lot of different aspects to it. For example, modern style could be like a bit bright, light, like a lot of space. Traditional maybe a bit darker. So I think right now, in terms of our language, when we say style, it's very kind of, it can like maybe capture a lot of these different clusters together into one meaning. So the idea, the way to go forward is maybe like kind of to separate into more kind of low level definitions of style. And then maybe with those lower level definitions, we may go forward and kind of use something similar to what you explain. The problem is it like, I'm not sure what those lower level definitions would be. It's difficult. Like
Yeah,
how
I
would
agree. Yeah.
yeah. So it makes sense, but it's very kind of hard to kind of just define, even like on like to agree between us what is like a style. So
See. Also, I'm not sure if are you so do you work with Masaki? Because I just think this kind of technology is going to be very attractive to him. Yeah.
So yeah, so in regards to Masaki, I did work with Masaki before. Right now, I'm not sure what he's working on. Like I know he does have his own company, and you know he's successful, and so maybe he's like more focusing on that right now. But if he would like to at some point kind of do more on this side, then sure we can do that. So I'm not
Yeah.
like I'm not this is more like of a time constraint, right? Like we only have so much time. So
Yeah. So I guess any other question from the audience? Yeah, I'm definitely happy to discuss with you more during our one-on-one meeting. I think
sure.
I mentioned Masaki is because I understand he's working on also style related problems, but more on custom rather than furniture. So I think
More on what? Clothes?
customs, yeah, clothes,
Costume.
yeah,
Yeah. So it's very related. But there are differences, right? Clothes is usually like I think it's a bit cleaner in a way. Um, you can actually kind of separate different clothes from each other, maybe a bit more easily. Rooms are a bit more complicated, I think. Kind of interiors are a bit more complicated because you have more aspects such as like light. For example, if you just have a different light, the style could appear to be something completely different. Or if you have more space, or if you have like so different kind of modalities kind of really affect how much we think of the style. So it's similar, but it's a bit different. And like a lot of actually research work that I saw that tried to deal with this from like computer vision aspect and all of that, they actually do experiments both on furniture and on cloth using the same framework. So we'll see. I don't know. Like it may work, it may not. It's complicated.
okay. Okay, so yeah, I guess we can continue with more discussions. Oh, I think there's another question from Logan. So do you think your method of grouping different styles of images could be applied to text? For example, grouping together slang text versus formal text.
So in terms of the grouping, do you think the method of grouping different styles of, so are you saying like, let's define a style for text. So all of this text is slang and all of this text is formal. I don't see why you can't do that. You can just define a grouping. Why not, right? And you can just, I'm not exactly sure what kind of task you have. Maybe you want to classify if it's like slang or formal. So you definitely can do that. Yeah, I'm not sure. I'm not exactly sure if that's what you mean, or you have a different question, Logan.
Sure. One thing I was reading a couple of weeks ago was a paper that was describing a way to group different unstructured data sets of text that are mixed between formal and informal text. And I was wondering if your method of being able to have different texts that relate to each other, or sorry, not text, images relate to each other, could also apply to a text data set as well.
Yeah, so as long as you have a way to create this kind of for each of your input text or input groupings of text, as long as you have a way to create these kind of like a network you classify the network, you have a network to train on certain tasks, and then you have this kind of embedding space, then you can use this embedding space in a way to kind of find similar style text or similar style or similar whatever text that you're trying to find, I think it's worth a shot. I'm not sure if that's exactly what you're trying to do, but this machine learning is not just image specific and can be used like anything that you in any kind of neural network, a deep learning scenario.
Yes, thanks. And I think Logan's question is also very relevant to my question. So over there, indeed, because I think slang versus not slang, that's more binary than style of furniture. So over there, sometimes I do believe people may think about disentangling the representation into, the slang specific part and the other purely semantic part. And use that to support slang generation or whatever end task it is. Yeah. Okay. Yeah, but that's a great question. So any other questions from the audience? Okay, so I guess we'll meet in an hour and have more discussions. And I think if there are more questions from people in ISI and USC other departments, we'll send them through email to you.
Okay, sure, yeah, and that's my email over here.
Okay.
Okay,
Yeah.
great. Thanks. See you soon.
Okay, thanks.
Okay.
Bye.
I'm gonna quit now. Bye.